Welcome back to our podcast, and this week we're going to be taking a look at some of the nonmetals. So, mine's first, so I'm going to start off. I'm doing phosphorus, which was, well, as far as when it was first isolated, there's a small chance that Arabian alchemists isolated it in the 12th century, but no one really knows for sure. But we do know that a German merchant isolated it in 1669 named, I'm sorry if I pronounce this wrong, but I think it's Heinig Brand, possibly. I think that's what it is. But anyway, and it's the 12th most abundant chemical in Earth's crust, which is pretty cool. But what I really wanted to talk about, because I don't think we've really had a chance yet, is that phosphorus has different allotropes. And what allotropes are, I had a definition that I thought was pretty good up here, but I can't find it. So, allotropes are basically different physical forms of an element, or different, ways that they bonded together, sort of, that make different kinds of elements. But for phosphorus, there are three main types that I'm going to go over today. There are at least 5, but I'm just going to go over white, red, and black, because those are the main ones that are most used, and it's easier than going over 5, because I don't know if you'd want to listen to that many, and I don't know if everyone wants to explain that many, so I think we're just going to go over 3 for now. But the first one I'm going to go over is white, because white's the most reactive, it's the most explodey, it's the kind of the cool one. And it's very toxic, and it's supposed to have a very pungent, almost garlic-like odor. And when it's at room temperature, it's like a waxy, translucent solid. So if you can kind of try to envision that. And like we said, allotropes are different ways that atoms bond together. And so the way that white phosphorus looks, it's almost like a 3D triangle made of 4 phosphorus atoms. So you have 3 on the bottom, and then you have the one on the top. If you want to look up a picture, that might be easier as well. But that's what that one looks like. And what I think is really cool about it is that it's very unstable in air, so it will pretty much spontaneously ignite when it's exposed to air. White fumes will come off of it first, and it will burst into flames after, but it happens so fast that it seems spontaneous. And it also glows in the dark, which I just thought was a really cool fact to just add in, because why not? And another way, it's different from the one that I'm gonna go over next. So it doesn't dissolve in water, but it does dissolve in something called carbon disulfide. The next one is red phosphorus, and you get it by heating white phosphorus at 573 degrees Kelvin in an inert atmosphere, which means, pretty much like a non-reactive atmosphere, like noble gases, which we're going to go over in 2 weeks, or possibly next week. But you do this because if you tried to heat white phosphorus in a regular atmosphere, it would explode, which is why you need the inert atmosphere so that it doesn't do that. And so red phosphorus, as you could assume, is red. And it's supposed to have an iron gray luster on it. And the cool thing about, well, not really cool, but it makes it easier to explain, but the way that red phosphorus looks when it's bonded is pretty much just a bunch of white phosphoruses bonded together. So if you zoomed in on red phosphorus, it would look a lot like white phosphorus in the sense that there's a bunch of pyramids, but they would all be connected together. And it's not as reactive as white phosphorus. It does not glow in the dark. It's not toxic, and it's odorless, so it's very different, which I think is cool because they're very close in the way that they're bonded together, but there's so many changes that happen because of the way that they bonded, which just makes me, I don't know, it's just interesting to me. And then it does not dissolve in water or carbon disulfide. And that's pretty much all I had on red phosphorus. It's not super exciting. The most exciting one is definitely white phosphorus. And then the last one that I'm going to go over is black phosphorus. And there's actually 2 types of black. There's alpha and there's beta. So if you heat red phosphorus at 803 degrees Kelvin in a sealed tube, you get black phosphorus. But if you heat white phosphorus at 473 degrees Kelvin under high pressure, then you get beta black phosphorus. But I think they're very similar. They're not super different. They're both black phosphorus. And the way that kind of looks is they almost look like polymers, I want to say. It's kind of, if I remember correctly, it's just a bunch of like hexagons put together. It's a lot like how you would think a polymer would look. It's easiest to find information on white because it's the most exciting and everyone wants to learn about it because it explodes and it's just cool. And when you get to black, there's not much information that's like readily available about it, but it is the most stable, so it's not going to react as easily as red and white are. And there really wasn't that much for black as far as like information went. That was pretty much all that I could find. But a cool thing that I thought phosphorus was used for is matches, actually. So if you think about a safety match, it's like a stick with a red head on it, and what that actually is the match head has red phosphorus on it, which is not the one that ignites when it is in contact with air. But what happens is when you strike the match, the friction between the match head and what you're striking it on causes it to heat up, which is why the matches are kind of sandpapery feeling. And when you have that sheet of, I think it might actually be sandpaper on the box that you strike it against, you need that friction because otherwise it won't work. And that's because you need the heat from it. And what that heat does is it actually changes the red phosphorus to white phosphorus, which ignites in air, which is how you get the fire. But there's also way more to a match. That's not just how a match works. You also have like the oxidizers and the molecules that make the flame last longer, because if you just had the phosphorus, it would just be there and it would be gone, and it would be as great as it is, which is why we have the oxidizers. I think I said that right? Yeah. But this is basically how phosphorus is used in matches. They have the red phosphorus, which is heated up to create white phosphorus, which kind of starts the flame which you see in a match, which I just thought was interesting because I kind of wondered how matches worked for a little bit. And yeah, that's mostly what I had on phosphorus.
Well, I've always wondered how matches work as well, but I've been too lazy to actually do the research myself.
I did the research like 10 minutes ago, so it's fine.
Alright, so moving on to sulfur, which is element 16, which is directly right next to phosphorus, to the right of it, and right below oxygen. If any of you are looking at your periodic table and want to see it, it is a bright yellow solid at room temperature, and it was discovered really, really early on and was used by many ancient civilizations. I'm not huge, I don't have a lot of biblical background, but they do make references to it in the Bible. Even when they say brimstone, that's actually them referring to sulfur. I just thought that was kind of cool. So it makes up about 0.05% of the universe, which sounds small, but considering the entire universe, that's actually a large quantity. And especially for an element of its size. So more than 1 or 2 protons, pretty much, since the majority of the atoms in the universe are hydrogen, which is just a proton.
Yeah.
It makes up 0.042% of the Earth's crust and 0.093% in the ocean, which again sounds like a really small number, but considering the entire size of the Earth, that's actually enough to make 3 moons made out of sulfur. That amount in the Earth's crust that we found is actually thought to be from volcanic origin. So they think there could actually be more further down, deeper into the Earth.
Like the mantle?
Not quite into the core, but further down the crust where we haven't found it, not directly
Like the mantle, or
I don't know if it's the mantle, because the mantle is more liquid.
Yeah.
Or liquidy.
But
so I think it's just further down. It is actually also one of the few elements that is found in its pure form in nature, so not actually bonded to some other compound. It appears and is used primarily in a lot of other compounds, but it's unique in the fact that you can actually find pure sulfur. And pure sulfur is actually odorless, which I think is interesting because it's notoriously known for its bad smell.
Yeah, because if you have like a sulfur leak, you know it smells bad.
Yes, and I will talk about that eventually. But we kind of use sulfur primarily in like some explosive things as well, like gunpowder and fireworks. Even found in some matches as well. It's not like he talked about the whole phosphorus thing, it's just kind of within them.
Yeah, it is used with them. I read about that briefly, but I don't remember what. Yeah.
Yeah, and then it's in like pesticides and fertilizers and such, but its primary use is in compounds. So actually a fairly interesting thing is that in organic chemistry, which is basically the study of carbon, because carbon can do 50,000 things. So they actually, since carbon can do 50,000 things, like I just said, there's lots of like variations of different like additions to the carbon compounds, I guess you could say, which are called like functional groups. And so functional groups that contain sulfur and hydrogen are called thiols, which is THIOL, thiol. Just because it's... So since sulfur is below oxygen, it's in family 16, that means it has two valence electrons, so it can form two bonds, or two covalent bonds, or in other words, it can share those two electrons with up to two other atoms. So in a thiol, it would share one electron with a hydrogen, and then the other it would share with a carbon atom, so that you have this branch of a sulfur and a hydrogen on your carbon chain. Which brings me to my joke that I made up in organic chemistry, which kind of really made me crack up more than I should have, because it's a really bad pun. Since the atomic symbol for sulfur is S, and the atomic symbol for hydrogen is H, we put SH together. And I said, so what does a thiol say in the library? Yes.
We love chemistry jokes.
I felt so proud of myself when I made that up. And yes. But thiols in organic chemistry, those are those notorious, really bad smells. Due to the sulfur on the molecules. So smells like garlic, wet dog. You have a dog and you know the wet dog smell. Sweat or body odor, asparagus, rotten egg, natural gas. The natural gas smells actually because they add those thiol compounds to the some alkane compound. I don't know which one it is. Like you have a gas stove. They add that there because your brain can recognize, oh, those unpleasant smells is probably toxic or bad. Shouldn't be inhaling that.
Or like if your gas is leaking so you don't light something.
So they add it because your brain can recognize it's a bad smell, so you know to turn it off, since the natural gas that they use doesn't have a smell, so you could accidentally blow up your house by accident and wouldn't know because it had gas in it, which is bad. But yeah,
yeah, if you're smelling that smell, it's something bad. It's not usually anything good.
But yeah, it's interesting because your brain can recognize this as toxic smells, but sulfur itself isn't that dangerous. In fact, you need some sulfur in your body to be alive. It makes up like 0.2% of the human body. However, there are, some very dangerous compounds. For example, hydrogen sulfide. I have a story with this one. So hydrogen sulfide is very toxic. 800 parts per million for 5-minute exposure is lethal for 50% of humans. It causes respiratory failure, and moderate exposure can cause headaches, dizziness, nausea, vomiting, coughing, difficulty breathing. So, to my story.
Seriously, this sounds like a great story.
It's actually kind of a boring story, but I wanted to share because it's my experience with hydrogen sulfide and the time that I inhaled hydrogen sulfide.
I mean, it can't be that boring.
So, okay. My family was visiting Yellowstone, and Yellowstone, they have these areas with like a bunch of mud pots, which are actually really cool and fascinating. And Yellowstone in general is really fascinating geologically. But these mud pots are essentially there's these steam vents from under the Earth's surface where you have like a bunch of the steam escaping, and it's like around 280 degrees Fahrenheit. And you have the sulfuric acid dissolving rock and clay, which creates this really muddy liquid pool that bubbles and smells absolutely horrendous because you have hydrogen sulfide coming from it. And, it's a really big tourist attraction. And it's perfectly fine, like, the amount of exposure that you can see there. So my family was visiting it, and we stopped at some of these areas, and I was having a lot of fun reading about, the hydrogen sulfide and sulfuric acid dissolving the clay and looking at it. And there was even this cave-like thing, which I assumed was probably the acid had like corroded the rock to create this cave-like thing. And there was this like cloud of gas that was coming from it. And it looked really cool. It was called like Dragon's Breath or something. It had this really cool name, and it was really fun. But then I started to feel a little sick to my stomach. Yes, I did, and I was not having a good time with that. So I went to leave the area because I was like I couldn't do it, and got this big whiff of some gas, and it just stuck there at the back of my mouth, and I almost threw up right there. And I went straight to the bathroom, which was this like outhouse thing that just smelled even worse because you have all the human waste smell on top of the hydrogen sulfide smell. So I was like, yeah, no, can't stay here. Meanwhile, as I ran away to the outhouse, my family had gone off on this trail, and I couldn't find them. So I went to the car to think that maybe I could avoid the smell in the car, but the car was locked. So I had to stay out there, feeling like getting all of those, hydrogen sulfide exposure symptoms. Just sitting on the car like I'm going to die. I hate my life. What am I doing? And it felt like I had to wait for like a half hour. It was probably like 10 to 15 minutes until my father with the keys finally came around and unlocked the door. And we had this like bag of gummy bears in my car. And I just immediately just ripped open the bag and just like stuffed my entire face in it, trying to just get that smell out of my system. It kind of worked, but that smell stayed with me for like a day. Could not get it out. I was fine. I didn't die. I'm still talking, so I'm pretty sure I'm still alive. But needless to say, I kind of despise the smell of sulfur and hydrogen sulfide, and I would really advise you to not take a whiff of that. It's very unpleasant.
So yeah, the moral of the story is if you're going somewhere with lots of hydrogen sulfide, make sure you don't stay there for too long, and also make sure you have a key to your car and lots of candles, and you should be fine.
Yeah. Well, actually, hydrogen sulfide is combustible, so probably don't bring the candles.
Yeah, maybe not candles. Maybe like essential oils or something. I don't know. Something that smells really good.
Yeah. Oof. It's not fun. I'll just say that. I had it like in the back of my throat for like, even like we left Yellowstone. We were in like this city. It's not really, it's in Wyoming. There's not really a city there. It's very, it's like a small town. It was still like, I could not get it out of it was just forever scarred in the back of my mind.
If I ever go to Yellowstone now, this is all I'm going to think about.
I mean, it's really cool. Like, I was kind of like disappointed because I wanted, like, there were like so many like things to like read about on like those, about the mud pits and everything. It was really fascinating to look at and just to be there, but I couldn't handle it. Anyhow, yeah, that's what happened in Sulphur.
That was not a boring story.
Okay, well, I mean, because like I didn't go to the hospital or anything.
That's true.
Kind of like uneventful. That's why I said it was kind of boring. But
nothing exploded. No one went to the hospital. So I mean, sometimes.
Yeah, and yeah.
So yeah, on that note, thank you. Yeah. Thanks for listening to our podcast, and we hope you'll join us next week where we're going to talk about some more interesting elements.